Homework Solutions 6.6, a 20 kVA, 8,480 volt single-phase distribution transformer has the following parameters. R1 equals 32 ohms, R2 equals 0.05 ohms, XL1 equals 45 ohms, XL2 equals 0.06 ohms. If the transformer supplying a 0.8 power factor lagging load at rated kVA in voltage, what is the transformer's primary voltage? Utilize the simplified practical transformer model. So in this problem, we are given that the three-phase power that not the three-phase we're analyzing single-phase transformers, aren't we? The single-phase power that this transformer can deliver is 20 kVA. And we are then told the turns ratio, NP to NS, is 8,000 to 480. We were then given the primary characteristics. R1 equals 32 ohms and XL1 equals 45 ohms. And the secondary characteristics are R2 equals 0.05 ohms and XL2 is 0.06 ohms. We were then told that the transformer supplying a lagging load at 0.8 power factor, rated kVA, rated voltage. So I'll modify that. That is PF equals 0.8 right there. We are asked to find the input to the primary necessary for this. So find the primary side voltage. So again, we need to draw the practical transformer model, the simplified practical transformer model. We've got the input voltage to the primary side. So everything beyond these terminals represents the primary side of the transformer. That is, this is a resistor, believe it or not, 32 ohms. This is J45 over here. This is the input impedance of the primary side. Then we've got our ideal transformer right there, plus minus VP prime. Here's our ideal transformer. It was 8,000 to 480 was the turns ratio. The secondary characteristics were 0.05 plus J 0.06. That, and then we've got some load. We weren't told the impedance of this load. We'll just call it ZL. And we were told that the load consumes rated power, so that's 20 kVA at 0.8 lagging. And we were told that it was supplied with rated voltage. This was an 8,000 to 480 volt transformer, so that's plus minus 480 volts at angle 0 degrees. We'll use that as the reference. So that's the circuit we have to solve, and we need to determine VP here. So the technique again is that we can refer all of this stuff in the secondary circuit over into the primary side of the circuit. We can't directly reflect the impedance over because we don't have one, so we can try to determine, or what we'll do is we'll use the rated kVA and voltage to determine what the current flow in the secondary is, and then we can also determine what the ZL prime is. So once we know that, we can figure out what the voltages in the primary are. So I can determine ZL prime from the relationship that the S in the load there is going to be equal to the magnitude of the voltage across the load divided by the complex conjugate of ZL there. So ZL star is what that is right there. So I can solve this for ZL star. ZL is equal to magnitude of V squared over S, and then we need to take the complex conjugate of that to get ZL. And so this is going to be equal to 480 volts, magnitude of that squared, divided by 20 e to the third at an angle of, and I need to take the inverse cosine of 0.8. That's 36.87. It's a lagging load, so that's minus 36.87. And then I need to take the complex conjugate of that. So I get a load impedance here of 9.216 plus J 6.91 ohms. So now I know this and I know this. I can refer them to the primary side. The problem is then I just know the impedance is there. So somehow I need to calculate the voltage across the primary terminals here. I can do that if I know the current flow in the primary, right? I can just multiply current times the sum of these plus this thing referred to the primary. So how do I get current flow in the primary? Well, I can calculate it in the secondary through this load because I know voltage and impedance. If I do that, then I can refer the secondary current to the primary. So I'm going to say that the secondary current is equal to the load power divided by the load voltage. Take the complex conjugate of that. I could have used impedance and voltage, impedance and power, any of the formulas you want to use that relate power, current, and voltage, whatever, for complex systems. That's fine. They should all give you the same answer. I just happen to choose these. So again, I'm at 20 e to the third at an angle of negative 36.87. I need to divide that by 480. Then I take the complex conjugate of that to get my current, and I got 41.67 at an angle of negative 36.87 degrees, which I just noticed this is a mistake right there. That should be a plus. Power triangle for a lagging system looks like that, right? S is in the first quadrant. So if I'm going to use the complex conjugate there, that needs to be positive. I combined two steps and didn't realize that. My apologies right there. So hopefully that clears up that confusion. This answer is correct, though. I just had marked the wrong symbol right there. So 41.67 angle negative 36.87 degrees amps for the current in the secondary. The current in the primary is going to be equal to the current in the secondary times NS over NP. So that's 41.67 at an angle of negative 36.87 degrees amps times NS, which is the secondary number of turns, divided by NP, the primary number of turns. And so that gives me a primary current of 2.5 at an angle of negative 36.87 degrees. Right, this was a step down transformer. That means the current in the primary needs to be smaller than the current in the secondary. So that looks good. Okay, so we've got that. That's the current flow through this branch right here. So I can say that the circuit that I'm solving now looks like this. ZP, and then I've got ZS prime plus ZL prime. That's primary current. That's VP. So VP is just IP times ZP plus ZS prime plus ZL prime, where these have been referred over. So I've got that. I don't know these values yet. I haven't calculated them, right? I've got ZL and ZS, but I need to calculate what they are. So ZS prime is going to be NP over NS quantity squared times the transformer's secondary impedance. So that's equal to 8,000 over 480 times, go up to our circuit model there, 0.05 plus J 0.06. So that's going to give me a ZS prime of 13.89 plus J 16.67 ohms. ZL prime is going to be NP over NS squared times ZL. So that's 8,000 over 480 times that value right there, ZL prime, 9.216 plus J 6.91. And so that gives me 2,560 plus J 1919.4 ohms. So my dot got kind of lost there. So 13.89 plus J 16.67 for ZS prime, and ZL prime is 2,560 ohms plus J 1919.4 ohms. Primary side voltage then is just the current times the sum of all these. So the current we calculated right here, 2.5 at an angle of negative 36.87 degrees amps times all of this added together. So the ZP comes from our circuit model. It's 32 plus J45 is the primary side impedance of the transformer. 52 plus J45. Oh, I don't want to close those parentheses. Plus ZS reflected plus ZL reflected. So this gives me the primary side input voltage 8183.62 at an angle of 0.37 degrees volts. So that's my input to the transformer. Primary will allow me to operate this transformer at 480 volts output, delivering 20 kVA to a 0.8 power factor lagging load.